Hi class. In this lab, we will do a copper recovery cycle. So we will start with copper. So we will start with copper, and we will do a series of chemical reactions and to convert this one to the solution. And finally, we will regenerate the copper. And in this case, we will test the law of conservation of the mass. Say you starting with this much, say how much you can recover in that. Then we also remember every step of chemical reaction. So every step of chemical reaction, you cannot get 100% of yield, right? So assume you have, say, 90% of yield for every step. So this one roughly will give you 5 steps of reaction. So you have 90% and multiply 90%, then multiply 90%, then multiply 90%. Then you will do multiply 90%. You can imagine how much you can get. So normally every step reaction, if you can get 90%, the yield is already very high. So hopefully you will get something like 4 steps for like this. So you will get roughly, if you have a 60% of yield recovery. For example, you start with 0.5 gram, then you will get something 0.32, 0.37 grams recovery. That's overall, as give you very good results, right? So let's see that. According to the law of the conservation of the mass, you see the matter or neither create nor destroyed in chemical reactions. So that means you how much amount you start with, you should have how much amount end with. What that means? So here we will talk about the mass. We will doesn't mean those mass will not change. So it does not mean mass will not change. It actually means that we will use, because we mentioned that in chemistry, most cases we will measure by moles, quantities. So if you start with how many moles, for example, here, how many moles of copper you start with, you once after reaction, you should have the same number of the coppers, you change the form. So either change it to this one, or if some change it to this one, but overall, if some still stay like this one, all put it together should give you the same number of that you start with. So that we talk about the conservation of the mass, right? Anyway, for the elements, we will look at the elements is a single pure substances that you cannot break that down further. So example like a copper, this one's a carbon and iron, aluminum, right? So the compounds can be a pure substances composed of at least 2 or more elements. Example, carbon dioxide, and this one's a molecular compounds. And this one, sodium chloride ionic compounds, right? So you can see that either one contains 2 different elements. This one's a carbon and oxygen. This one's sodium and chloride, different one. And you can see a lot of things. Let's see this one. Sodium perchloride. So this case, we have 3 elements, sodium, chloride, and oxygen, right? So you can see that. So for this recovery of the copper, we will involve 4 different reactions, and those we will consider them as a gas forming reaction. For this gas forming reaction, actually, you will see later, actually also can be considered as oxidation reduction. And this we also call that as redox. Simply write it as redox, right? So another one is a precipitation reaction. Precipitation reaction. This one normally generate substances was insoluble in solvent, right? And this also involve acid-base reaction. And finally, this one's a reduxation. So here we see this one, because gas forming reaction, we will see the details. Gas forming reaction can also fall into the redox reaction in this case. So let's see, how do we know the oxidation reduction reaction occurs? We will look at the change of the oxidation state, right? Oxidation state, this one indicates the extent to which an element is oxidized or reduced. So, for example, here, for the carbon atom, if we combust the charcoal, right? So this one, we will have coal, you can combust the coal or burn the coal. So with oxygen, you can see that. So go to, depending on the combustion conditions, with the excess amount of oxygen or not, you may have either carbon monoxide or carbon dioxide. Now, in this case, we can see for those that are simple elements, so their oxidation states are zero, right? So let's write on the right side here. So oxidation state is zero, and this one is zero as well. Now, in those compounds, you can see here, we can write an oxidation state as positive 2. Likewise, the oxygen will be negative 2, right? So we can write another way. So let's write it this way. 2 plus and 2 minus. Again, for this carbon dioxide, this will be 4 plus, and this 2 minus was 2. So that's give whole molecule 0, right? Neutral. So oxidation state is a cytogenetical charge the element would have if all bonding or ionic. We assume they are ionic. They would be neutral overall, right? So oxidation is the loss of electrons. So you can see from here, in this case, we say oxidation is a loss of electron. This one generally apply for the metal. For example, we have the example here. Iron plus hydrochloride, right? If we balance them, there you. Now you look at this one here, 0, this one go to 2 plus. So this lose 2 electrons. So this one, and likewise here, proton that's positive, and this one 0. So this one gain electron. So here we can see the loss of electron or reduction to gain of electron. So the proton is reduced to hydrogen, right? So that's gain electron. For the case of carbon with oxygen, here we will not actually see the loss of electron, but we do see the change of oxidation state, right? So that's a different way to tell that's an oxidation reduction reaction. For the case of copper, so this one, that's a transition metal. And with significant commercial importance, this one, because we know the reason for that is copper is a good conductor. So it's a good conductor of the electricity and also heat. So that's how we often use copper for making the wires to conduct the electricity. And you can open your electric device. You can see that inside there are so many the copper wires. That's for the conductivity for electricity, right? But for the copper in the elemental form, that will be this one has an oxidation state of 0. This is we normally set all those at elemental state of 0, right? So this case, for the copper, we know their electronic configuration or electron configuration that we let's write that from this way: 1s2, 2s2, right? 2p6, then 3s2, 3p6, then 3d, 10, 4s1, right? So for this case, we can allow them to lose the outermost share of electrons. So they lose one electrons. So from copper 0 to copper 1, so that's how you can see lose this one. By the same time, this one, since that's a p orbital electron can also be lose 1 or 2, something like that. So this case, if then lose 2, then you will see that form that. So this case, we can allow them to write it here. You can see 1s2, 2s2, 2p6, 3s2, 3p6, 3d9. Now that will be the and you can further lose to give this one, but this is very high oxidation state. So those are the not common in chemistry. Now, the objective of this lab is to practice the quantitative laboratory techniques. So you will try to manipulate your lab and then say just to lose as little as possible. You don't want to lose any mass because you want to have a very high recovery yield, right? And also we will test the law of conservation of the mass. Then we will do that is convert elements into the compounds. Basically, copper, we know that it's metal, not soluble in water, but we will try to convert them into soluble in aqueous solutions. Then we will separate the compound into their constituent elements. Finally, we will convert those compounds of involving the copper elements back to this copper again. So we will perform a sequence of quantitative chemical reactions. So we call the quantitative chemical reaction is we make sure every step's conversion 100% in completion. Well, we will call that as quantitatively. In this case, every step the yields are close to 100%. But saying that is 100% not a guarantee we have the 100% of the mass recovered because, for example, when you do the filtration, so for example, you have so here we use a Bush funnel and we put it on a flask bottom attached to vacuum. And you use a filter paper like this one. Once you put the mass on top and the liquid filter off, the question is you probably, even your reaction is 100% complete, but you still have some mass will be in return at the filter paper. You will not 100% remove them from the filter paper. So that's you want to do something there. So a compound is comprised of two or more elements we already mentioned earlier, right? Elements constitute the fundamental building blocks. So let's see that individual steps. So the first step is to convert the elemental copper into solution. For this case, you can see we will convert this, so that's the first step, right? Convert to copper nitrate. And then this nitrate will be in aqueous solutions. Then we will change them at the base, allow them to precipitate. So this become a solid. And this solid, we can from here, we can simply react with the sulfuric acid to form the copper sulfate, but we simply heat them, do that decomposition, allow them to generate a copper oxide. So this one also solid. And after that, we change to copper sulfate. Then this one, we will reduce that to copper again. So you can see we have a total of 5 steps reactions. And every step we will look at the detail on next slide and the following slides. So the first step reaction is convert the elemental copper to the copper, the 2, right? Copper 2 nitrate, or you can call that as a copper nitrate. So this reaction will treat this one with the nitric acid and they'll convert to salt and they generate nitric dioxide. So this one we call gas forming reaction because you see this one actually is the gas evolving from the aqueous solutions. So you can clearly see the color of this one. So that's the brown red color of this one. Now remember, this one is the toxic gas. Why this one is toxic? Because this one combines water will generate nitric acid again. So we know this acid is toxic. So this step we have to put in the fume hood. Fume hood. We have to do that in the fume hood. Okay. So now this reaction is already balanced. You can see that. So this one is the example gas forming reaction, but also is a reduction reaction. So redox reaction. The reason we call that, you can look at that here. This one oxidation state is 0, right? But here you see that it changed to 2 plus. Likewise, for the nitrogen atom here is 5 plus. Now it's changing to 4 plus, right? So that's how you can see the oxidation state changes. So that's how we also call that as a redox reaction. And this one is oxidized to 2 plus. But then nitrogen 5 is go to nitrogen 4, right? So you see here, remember to weigh your starting amount of copper. So you need to weigh them how much you use that. And let's see here, this one, we know what's the color of copper looks like. But once I change it to the solution now, this one become a copper. So let's see that change to this one now in the aqueous solution. So here's the aqueous solution. So actually associated with, you can see what form this form. So there's associated water with that. And this will show the color of blue. So you will see the blue color. Now for this reaction, you will so record the case steps and the observation. That will ask you to observe the color change and the what the gas evolve, the color of the gas, or you see the bubble generated or not. And so you see any precipitation or not, and observe anything else, right? And then you will weigh the copper, like we said earlier, you need to record them. So this one clearly record how much. And then you add the nitric acid in the hood, film hood. We mentioned that film hood. So then if this add the nitric acid is not enough to dissolve all the coppers, then you need to add more, roughly about 2 to 4 milliliter more for that. And then you record the observation again and say how much nitric acid you add total. But after that, after this is finished, you need to slowly add the water. The reason for that here, for this oxidation reduction reaction, we mentioned the previous slide to convert that to copper nitrate, right? This one, it's oxidation reduction. So we want to concentrate it. This one, higher the concentration, the faster reaction. If you start with water dilute, then the reaction is very, very slow. So only after the reaction finish, we added the water to dilute it, right? Dilute your solution. Allow that for the following reactions. For the second reactions, we convert the copper nitrate to copper hydroxide. So this one, actually, you see this one is a, we will say precipitation reaction. Here is an aqueous solution that's soluble, and those sodium hydroxide also aqueous soluble. But here you see that's solid, that's the insoluble. So you form the precipitate, right? Now, so this equation also is balanced. This one will be an example of the precipitation reaction. And here, sodium hydroxide, so this one, sodium hydroxide, is a strong base. Now, this one will show bluish green color. So that one will precipitate. And so in order to make sure all of those precipitate, you will make sure there are in excess amount of sodium hydroxide in presence. So because if this one is not enough, then there will be some of this left in the solution. And in this case, you cannot tell, even you see a lot of the precipitate, like some kind of, here we mentioned that the bluish green colored, those precipitate. It's difficult to tell you have all this completed convert. So only way you can make sure that one is you have enough amount of a base to allow the reaction, drive the reaction all the way to the right side, right? So how do we know we have excess amount of sodium hydroxide we can use the litmus paper that will show the red color. That will tell you have excess amount of hydroxide in the solutions. Then that will make sure this reaction is finished. Then, so here, we will use the stir rod to dip in the NMR flask and dip a little bit to the litmus paper. If that shows the red colors, so solution will, so this litmus paper that in the show red if acidic, but it will show dark blue if basic. So you will change them, make sure that will show the blue, then that will be basic. So if if you see the color is somewhere like show this color, this is something close to neutral. So if you see the color something like that, it's neutral. But then you need to add the one more ml of the sodium hydroxide and test again, and so record how much sodium hydroxide you add, and so. And this allows you to do the calculation. For example, you can see how much hydro on nitric acid you use initially. You can calculate the number of moles, and then later you can calculate the number of moles of sodium hydroxide. See if this one is more than that, that's certainly you have reactions. That is enough. If this one is much less than that, that's you can find out how to justify your observation. Now, the third reaction is to convert the copper hydroxide to copper oxide. This one we simply apply the heat. So that you see, maintain the temperature just below at the boiling. Just you have the, remember you have this one in the aqueous solution. That's you want to heat them until your water is about to boil. A little bit of boiling. You see that. Make sure you add the boiling chips to avoid the bumping, prevent the bumping. This case, you can see the color will change to black. Somehow you will see the black turn to black. That indicates, make sure once you see the black, then you will hit a little bit further. Now, this fully converted to the copper oxide, right? So to do this, we will add the 2 to 3 boiling chips. Boiling chips are very small particles. You don't need a lot, small, just 2 to 3, that will be enough. Then you heat them, right? And after that, you turn off the Bunsen burner, make sure that's cool, and you will do the recorded observation. Make sure that's cool. You cannot transfer them during the hot solution to do the filtration, because remember that even we mentioned either of this one or copper oxide, we mentioned they are insoluble in water, but since you use the water close to boiling, so hot water in this case, well, their solubility in hot water will be higher than when they are in the water of low temperatures. In this case, if you filter them during the hot, you will lose a lot of them because they will go through the filter paper along with the hot water. So you will make sure them cool close to when you use your finger to touch the outside of the NMR flask. You don't feel that hot, just a little bit warm, and that's about to filtrate that. For the filters, right? So I would recommend that you use a Bush funnel, something like this, and something like this to do the filtration, small as possible, because you don't have much materials on the bottom here. Then we attach to vacuum, right? So after that, you will, so since your solution is in the NMR flask, when you transfer them to here, you are not guaranteed 100% to transfer that. So then in this case, you will use water to flush them, allow all those particles will be transferred to here. In this case, we ask you to rinse those. After all transfer, we ask you to rinse 3 to with 5 ml of water for 3 times. This case, remember you have excess amount of hydroxide in your solution. In this case, we will wash something residual sodium hydroxide, because next step you will use acid to react with that. If there's a sodium hydroxide, that will cost some of your acid used, right? So this step of reaction, we will do that is to convert those here precipitate to solution again. So we will react with the high sulfuric acid. And this simply, you can consider this one the acid-base reaction. In this case, the sulfuric acid certainly is the acid, right? And the copper oxide, that will be base. So this will be the acid-base reaction, and to generate water and the salt. So the copper sulfate, that will be salt, right? So in this case, sulfuric acid will dissociate to give protons and the sulfate, right? So this one, you can see that process accompanied by a color change. Why? Because this one's black, we mentioned that earlier, and go to this one, that will form the copper, so that copper, so cation associated with the water, so they can associate with the 5 water, then you form sulfate, this one, and this one show blue color. Just like you see the color earlier for those one, right? Now remember this one, the color actually are almost the same like this one. It's a with the associated water. So for this one, you can see, remember earlier we have the funnel, right? Next this one, you filter that. I filter that. And here, this case, you can, once you dump everything, put another flask. Let me erase those things, right? Then we put a NMR flask here at the bottom, and the top, since that we can add the sulfuric acid to allow them to react to go to filtered here, right? So you pour the sulfuric acid to the solid, allow them to react. So this case, once they react, it will become soluble in the aqueous solutions, right? You can see that we pour through the funnel into the clean beaker. You can do that. And if not fully, you can continue add those things. But unless if your filter paper is not fully sealed and you have some particle easily drop here, then you need to repeat it again. So here you will record the observations and record the amount of sulfuric acid you use. The fifth step of reaction is convert the copper sulfate back to elemental copper, excuse me. So this case actually the oxidation reduction reaction. So we will call redox reaction. We use zinc paint to reduce that. So this case, you can see zinc, that's 0, right? Go to 2 plus. And excuse me, copper is 2 plus, go to 0. And also you see the color change during the solutions. Why? Because this one should blue color. You see. And in this case, that color is. And this one should shiny red, depends on how fast the reaction is. So this one is not soluble in water anymore. So we can isolate them and dry and away. So at this stage, you can compare how much copper you recovered, and based on how much you initially you can find the recovery yield. And in order to allow this reaction go faster, you will add some hydrochloric acid concentrate, because this one, the purpose of that, think about it, we use zinc, right? And then normally zinc are very reactive. So the surface, covered surface oxides to zinc oxide. And zinc oxide will protect the zinc. So in this case, if you simply put the zinc to the solution, to the copper sulfate solutions, there will be no reaction, right? So we need to add hydrochloric acid to remove the layer of those zinc oxide and use fresh zinc to reduce, right? If the solution still that until solution become colorless, if not, you need to add more zinc. Typically 2 to 3 pieces of the zinc pellet, that will be enough. And after the reaction, you need to decant the solution into clean beakers, and wash. And so after that, once you collect the copper, you can dry that with the paper towels and try to remove them as much as possible, from the paper towel and with that. So if the copper, remember, you recover that from aqueous, with aqueous solution, from aqueous solutions. So there's always a wet. You need to use a paper towel to dry that. Make sure the 2 times will be no different from, 0.01 grams for the 2 measurements, and that will record the amount of copper, recovered. So here you see, we assume all reactions are quantitative. That means they were 100% completion. So we can calculate yields, the actual yield over the theoretical yields. So for example, you start with 5 grams of copper. Theoretical yield, you should have 0.5 gram as well. But the actual yield, you may have 0.37. In this case, you can calculate the yield, right? So that's the actual yields. So how much you recover at the fifth step reaction. So, and the 100% yield, it never happened. As I show you, every step when you transfer the mass, more or less you will lose something. Particularly when you do the filtration, you will have something remain, or maybe not complete, transfer from the NMR flask or from the funnel.